Good afternoon all. What we're looking at today is lactate inflection point. Now it's been a little while since we've done a video, so hopefully you haven't missed me too much, but we'll see what we can do in regards to lactate inflection point. So it's a big part of our focus of our studies. We're looking at fatigue at the moment. We should be reminded that fatigue is multifactorial. That is, there's a lot of elements that contribute to the fatigue. There's the concept of fuel depletion, which should be pretty straightforward and basic for all of us, and that affects our ATP-CP energy system and our aerobic energy system with the depletion of creatine, phosphate, and the depletion of glycogen or fats respectively, but in most cases glycogen when we're talking about sport. The anaerobic glycolytic system though, it can suffer from the build-up of metabolic byproducts. Now the lactate inflection point is a measure of an athlete's aerobic capacity, because essentially if the aerobic system is the dominant energy system, well then lactate inflection point will not occur, because the lactate inflection point, as it very clearly says here, is the last point where lactate entry into and removal from the blood are balanced. So what that means is that the lactate production is equal to the lactate removal. So if you have a look here at this graph, we can see here that through this portion, although lactate production is slightly more than lactate removal, we'd essentially say that that's a steady state, in a similar way that we would talk about a slowly rising heart rate within a couple of beats per minute as being steady state. This point here though is of particular interest to us. You can see here that the speed is increasing along the bottom. So at this particular speed, the athlete has clearly shifted from having their aerobic system as the dominant energy system through this portion to now having their anaerobic glycolytic system as the dominant energy system. And you can see that as the intensity continues to increase, or the speed continues to increase, that the rate of lactate production is even more exceeding the rate of lactate removal. So what I've got attached for us now is a strange little video, and it's certainly one of the stranger things, probably easily the strangest thing I've ever put on YouTube. What we've got there are my feet. We've got a dish which will represent for us a muscle cell, and we've got a bowl of milk, and the milk in this particular instance is going to represent our lactic acid and hydrogen ions. In a moment you'll see one of my dogs, that one there that's starting to get a little bit interested. It's going to represent a mitochondria for us, and it's mitochondria that are responsible for processing energy aerobically. And essentially, when not enough energy can be processed aerobically, we have to start using the anaerobic systems, and that's when the buildup of lactic acid occurs. So you can see here that when I pour the milk in slowly, because the intensity is low, the lactate is easily removed. It's not a great camera angle, but you'll just have to believe me. So you can see there, the dog easily removing the lactic acid, or in this situation the mitochondria easily removing the lactic acid. However, as I up the tempo or increase the intensity, it means I have to increase the rate of lactate production. You can see here that all of a sudden the muscle cell is just starting to overflow. So essentially what we've simulated using the dog, the dish and the milk is this concept of lactate inflection point. So initially when I was pouring the milk in, we were working in this area here. Now all of a sudden we're working beyond our lactate inflection point, and we're now getting to call simply an overflow from within the muscle. If we continue on, you can see there that we're starting to spill the milk. Now this is where I want to start talking to you all about the lactate shuttle model. The lactate shuttle model is an important process that helps to minimise, I guess, the amount of time that lactic acid is present within the bloodstream. So what we try and do, or what the body tries to do, is rather than one muscle cell having to try and control all the lactate and hydrogen ions that are produced within that muscle cell, eventually gets to a point, the lactate inflection point, where it simply cannot be contained, and for lack of a better word, the lactate and hydrogen ions start to spill out of the muscle, the original muscle cell, and into the bloodstream. Now if we use the example of cycling, we can hopefully appreciate that when you're riding a bike, your leg muscles are working very hard, but your upper body muscles aren't doing as much. So it would be reasonable to assume that although your leg muscles might be producing vast amounts of lactic acid and hydrogen ions, your upper body muscles probably aren't. So with that in mind, wouldn't it make good sense to transport the excess lactate and hydrogen ions that we're producing, transport them through the bloodstream to other muscles in the body that are able to help with the processing of this lactate and hydrogen ions, simply because they're not working at a level that's producing too much lactate or hydrogen ions. So back to the video, what I've done is I've created another muscle cell by adding another dish of milk. So you can see here, another muscle cell goes down, You can see that there's a mitochondria getting ready and is very interested in assisting in the clearance of lactate. And that's essentially, if you imagine it happening on a grand scale of thousands to hundreds of thousands to if not millions of muscle cells joining in the process of removing the lactate. Bear in mind, of course, the lactate's not just being produced in the one muscle cell, it's being produced in just as, thousands upon thousands of muscle cells themselves. But the whole idea of the lactate shuttle is to essentially share the load. And by sharing the load, we can process the lactate far quicker than we ever would if we just left it to the one muscle cell or to the one group of muscle cells. By getting the whole body involved, or as many muscle cells involved as possible, well then obviously we're going to have a much greater chance of successfully removing the lactate and hydrogen ions from our body in a quick way. All right, you see there the dog's finishing off their drink. They were disappointed when that stopped being served up for them, I can assure you. So that's our lactate shuttle model, and that's our lactate inflection point in a nutshell. But I guess it's really important before we sign off to understand why it's so important for any athlete who's completed an event or a period of exercise that has had the anaerobic glycolytic system as the dominant energy system to conclude that effort with an active recovery. The active recovery helps to allow this system, this lactate shuttle model, to work more effectively. If you imagined yourself simply stopping exercise immediately, well then your ability to move that lactic acid and hydrogen ions that you've produced through the bloodstream is reduced, because by stopping, you're slowing your heart rate down immediately. If you continue to exercise, you maintain a higher heart rate, which maintains a greater amount of blood flow, which then allows for a more effective delivery of lactate and hydrogen ions to those other muscle cells that can assist in the removal of lactate and hydrogen ions. Also, the movement of the muscles is very important for venous return of the blood back to the heart, so it can be redistributed to these other areas of the body. Also, by increasing or maintaining a steady blood flow, we can actually then increase the oxygen delivery to all our working muscles, which once again allows for a faster delivery of lactic acid to those working muscles, but also a faster delivery of oxygen to those working muscles to assist in the processing and the removal of the lactate and hydrogen ions. I hope that makes sense to us all. It's a short little video, this one here. If you have any questions, by all means email me, but good luck for your sack later in the week.